photoemission and photoemission spectroscopy. Okay. All of you are familiar with photoemission, right? It is a story of 1905. That's more than 120 years old story. So I'll take you through this from that point, 1905 to till today. What are the developments? How this photoemission has transformed into a spectroscopy tool for analysis of materials, particularly solids. It can be used for liquids and gases also, but we will be focusing mostly on solids. Second. Yeah, this is the one, right? You have to show it here, huh? Oh, I see. Okay, okay. All right. Yeah, okay. So I have to show it here. It is working for you, not for me. Oh, okay, okay. Okay, okay. Now I understand. Oh, I see. Okay. So the arrows are, if you want to go forward, you have to press backward here. Interesting. Okay, all right, good. So if you see, let me start from this beginning. If you have a surface is kind of a solid. Let us say this is a surface. You want to see what is present on this surface. In the sense, we have a small, very tiny samples in the analysis. So on the surface, you can use all these particles. For example, in this case, some neutral atoms, ions, electrons, photons. All of these are probes. Basically, these probes go and hit the surface, and then they give out variety of things as they come out of the surface. One is if you use this some of these things, for example, ions, neutrals, if you use, you get this atomic diffraction, SNMS, TPD, etc. You can also get this. The photons are the ones which are interested. Of course, electrons also can be used to get some of these information. But what we are interested in is the photons. If you use photons, go impinge the photons on the surface, they actually give out electrons. And these electrons, if you analyze, you can get information about the what is present in the solid surface. Of course, if you use photons, you can also use, you can get reflection, Raman spectroscopy, X-rays, and all that. These are all variety of techniques that people use to analyze samples.
Actually, slides are not visible.
So we will be interested in XPS and Auger in this particular talk. And what it does is the science and application of XPS. What we are going to look at is the origin of that, spectral interpretation, chemical shift, binding energies, chemical state assignments. These are the things which we are going to spend some time on that. So if some of you are interested, photoelectric effect can be demonstrated. You can actually look at some of these YouTube. These things are now available. You can just click the YouTubes. You can get some information on the demonstration of photoemission. See, we have these beautiful crystals. You must have seen some of these crystals grow in the sea. And they have, I'm showing you here only the green ones, but there are blue, variety of colors because of the transition elements present there. For example, in this case, you have beryllium, aluminum, silicon, calcium, chromium, silicon. Different elements are there. How do we know such elements are present in these samples? And what are their oxidation states? All of us are familiar with oxidation states. What are their oxidation states? Etc. If you wanted to find out the best way, sorry. Oh, okay. Yeah, I think online also people are there, is it? Okay. Close this. Close that also. This one. I mean, you have to. No, wait. Just wait. This is the one. frequency you impinge on a surface, on a metallic surface, for example, cesium, and then you start seeing electrons coming out from that. Electrons coming out from that with certain kinetic energy. But then if the nu, if the threshold frequency or threshold energy is sufficient only, you can actually remove the electrons, or it should be more than that. If it is less than that, even if it is intense light, it will not give any electrons. So that is a simple figure that I have drawn here. So your h nu is nothing but work function. This is equal to work function. So h nu should be equal to work function. If h nu is greater than work function, then you start getting electrons with certain kinetic energy. Okay. So your h nu is a half mv square plus v. So this half mv square is nothing but your kinetic energy of the electron, wherever that frequency is high and you get electron kinetic energy is high. So this is the kinetic energy of the electron, and then phi is the work function. Work function is something which, you have a metallic surface, you have a surface, solid surface, you want to remove an electron. So you just can't pick up like a tomato from a bag. When you remove electron, there is a positive charge here. It will not allow the electron to go away. It will pull it back. So there's a certain amount of work has to be done for the electron to be free from the surface. It's a naive way of explaining it, but that energy is nothing but, you can call it as work function. Okay. So that work function plus kinetic energy of the electron is equal to h nu that you have used here. Okay. All right. If it is this is solid. If it is a gas phase, then this is nothing but ionization energy. You have a gas molecule or an atom, you remove an electron will come out. So that is nothing but ionization energy. When you remove electron from an ion or from a gas molecule or an atom, that is nothing but ionization energy, right? So that is ionization energy plus the electron energy, the electron that comes out with certain kinetic energy. So that is the expression. So E kinetic energy is equal to h nu minus E binding energy plus phi. In the solid, when the electron is coming out, you have energy levels are there. In the atoms, you have energy levels, right? So electron has to come out from one of the energy levels, and it has to cross the barrier and then go to the above the surface into the vacuum. So that means you also have information coming from binding energy plus the work function, both will be there in there. Okay, I'll just give you some examples here. So kinetic energy to h nu minus ionization potential for gas, kinetic energy to h nu minus binding energy minus phi for a solid. You should understand this one clearly. Binding energy refers to the electron coming from a particular orbital. Plus, since it is a solid, there is a work function, as I mentioned to you. So both it has to overcome. So that much energy is spent, and the remaining energy is the energy that is coming out, that the electron comes out. That is nothing but electron kinetic energy. So we need to measure this kinetic energy. You need to catch the electron, see what is the energy that is coming out. So these are some of the things. Since work function, I said different elements have work functions. For example, this is 4.08 electron volts. Normally in photoemission spectroscopy, energies are measured in electron volts, not in centimeter nodes like in IR spectroscopy and other spectroscopies. Okay. So aluminum has 4.08 electron volts, beryllium, cadmium, so on and so forth. Platinum has 6.3. So variety of work functions, phi values are varying depending on the material that you are looking at or metal that you are looking at. Interestingly, cesium is the one which has the lowest work function, 2.1. 2.1 electron volts is nothing but it matches with the ultraviolet radiation. If you have a UV radiation, you shine light on cesium, you will get electrons. UV, just UV light. You don't have to go to X-ray. UV light. Okay. So that is what is given here. Cesium metal, you shine UV light, you start getting electrons out. Start getting the electrons out. But then we need X-rays, because you need to remove the core electrons. There are other elements where, you just shine light UV, you will get only valence electrons will come out. Valence electrons have binding energies are very less. They are there in the valence shell. They easy to remove them. They are the ones which get involved in bonding. Valence electrons. But the core electrons need much more higher energy to get removed. So that energy requires X-rays. Okay, so you need X-rays. So X-rays can penetrate to the sample to the order of micrometer. Suppose I have a sample. If I shine put X-rays, they can actually penetrate about a micrometer length inside the sample. But these X-rays are not hard X-rays. These are somewhat soft X-rays, not very hard X-rays. Now, if you see here, the electron signal is obtained only from the depth of around 10 to 100 angstroms. I have a solid, I shine X-rays, I'll tell you the energy of the X-rays, and then electrons come out, and what is the depth of this sample from which the electrons come out? That depth is only 100 angstroms. 100 angstroms. Suppose say you have some sample here and below something else, it will not tell you what is below 100 angstroms. Only up to 100 angstroms only it will tell you what the story of the sample. It will not go beyond 100 angstroms, around 100 to 120 angstroms. That is something which you need to understand. That is why it is called surface sensitive technique. That is why it is called surface sensitive technique. Okay. Now X-rays, so these are the X-rays which are generally used. Magnesium K alpha, 1253.6 electron volts, very precise energy, because if HNU is precisely known, then only your kinetic energy can be estimated. Okay, this energy is precise. 1253.6 electron volts. Aluminum K alpha, this energy is 1486.6 electron volts. These are the two sources generally people use in the laboratory experiments.
But this instant energy is too high enough.
I will show you another diagram where you will understand better. The next diagram. Okay, I'll just show you that. These are required because to remove the electron from the core. Core requires a lot of energy. Core electrons. Whereas electrons, outer shell electrons means, for example, oxygen, if you take 1s electron, right? P electrons, D electrons, for example, in the transition matrix, those are all outer shell electrons. They don't require much energy, right? But if you go to very core electron, for example, gold, if you take 4f electron, this is a core electron. It requires more energy. There you need to have this high energy X-rays. These are not very high energy, but soft X-rays, I would call it. Okay. So normally sample will be radiated with photons of a single energy, that is either this or that. There are others also, but these are the ones generally in the laboratory people use only these two. So this is known as monoenergetic X-ray beam. This is monoenergetic X-ray beam. It has a precise energy. It has precise energy. So what happens when you shine X-rays? You shine X-ray, X-ray goes. These are the core electrons. You can call it as core electrons, which are very close to the nucleus. These are outer electrons. You call them valence electrons. Okay. Now these X-rays can go and knock out these electrons very easily. Of course, they can knock out these electrons also, but they can even go up to core electrons. So this is the electrons is knocked out. It comes out as a free electron. Okay, core electron. X-rays can also knock out valence electron. That is also there, right? But if you use UV light, UV light, it will knock out electrons only from the valence level, valence electrons. It will not reach the core at all. Core will not come if you use valence electrons. Okay. All right. So that is the so this is the nucleus, of course. This is the nucleus. Now, in addition to photoelectrons that are emitted in the photoelectric process, you also get something called Auger electrons, Auger electrons. Because of when the electron is removed, photoelectron is removed, the atom is excited, it is not stable. It tries to come back to the ground state. In the process, it can emit X-rays, or it can emit another electron which is called Auger electron. Auger. Okay. So that is another spectroscopy. That electron, if you analyze Auger electron, that second electron, then that will give you Auger spectroscopy. I'll just come back to you on this. Now look at this picture carefully. This is a very important picture, so that you understand any of the doubts also. Now I have a solid where I have atoms, right? The atoms have energy levels, 1s, 2s, 2p, so on and so forth. You can have 2s, 2p, 3s, 3p, 3d, so on and so forth. Okay. So you have these energy levels. Now what I am doing is I am using a photon. This is X-ray photon. I am using X-ray photon. This photon can actually go on core. It can remove the core electron, create a core hole there. Core hole there. Okay. So this electron comes out, and that if I analyze the energy of this electron, I get XPS, X-ray photoemission spectroscopy. Okay. Now if I use photon, this photon is not X-ray photon, but this is UV. Energy is of the order of UV range, around 40 electron volts to about 100 electron volts UV. If I use that, it will not have enough energy to knock out these electrons. It will remove only electrons from the valence levels. Okay, outermost levels. So that will give me ultraviolet photoelectron spectrum. Whereas this is X-ray photoelectron spectrum, that is ultraviolet photoelectron spectrum. This U and X are basically referring to this source that we have used, either X-ray or UV light. X-ray or UV light. Okay. Now come to this side. Now we have created this core hole, this one. Now since this once it is created, the atom is unstable. To make it little stable, electrons sitting in the higher energy levels can jump into this here, and then so that much energy is released from here to here. This energy difference is released. That energy can come out as X-ray. It can come out as X-ray. That is one process. Second process is that energy can be used to remove electron from a energy level higher than that here. Which one has a higher binding energy, this one or this one? This level or this level? This has higher binding energy. This has lower binding energy. That energy difference is the energy. That energy is used to remove this electron. It can be this electron also. I am just giving one example. There can be many levels here. I am just giving one example. So this electron is removed. This is called Auger electron, Auger. That leads to another spectroscopy called Auger spectroscopy. Auger spectroscopy. Not Auger, Auger. This is a German name. So that is the process. So now you see XPS and UPS. The binding energy of the electrons which are coming out here is equal to, for example, 1s electron. We have removed 1s electron. So binding energy of 1s electron is equal to h nu minus E kinetic energy. Kinetic energy is something which we measure in the spectrometer. Here, that work function we are not bothering, because work function we actually there is a way to avoid looking at work function, right? So if you keep that work function aside, essentially the h nu, that photon energy is equal to binding energy of the electron in a particular level plus the kinetic energy of the electron that has come out. That is what Einstein said. That's what Einstein said. He said in 1905. We still believe that, right? That's why the spectroscopy has come. Now here in AES, the electron energy, the Auger electron has an energy, that is kinetic energy. That kinetic energy is equal to energy of the 1s electron, where you have removed this, and then energy of the 2s electron, that is minus 2s electron. That difference is this one, minus energy of this electron, binding energy of this electron. So you would remove these three factors. What comes out is the kinetic energy of the electron, that is called Auger energy. Auger electron will come out with that much of energy. Notice that here h nu is there. What photon you are using matters a lot in XPS or UPS, but here there is no h nu here. Whatever source you use, the kinetic energy of the electron, the Auger electron is going to be fixed. Okay. Incidentally, in Auger spectroscopy, people don't generally use photons; they use electrons. That's a different story, but yeah. Okay. So photoelectron spectroscopy is X-ray and UV induced, and Auger electron spectroscopy AES. XPS and UPS are both single electron process, whereas AES involve 3 electrons. 1, 2, 3 electrons are involved in Auger, whereas this one only 1 electron is involved. The 1 electron process, 3 electron process. All right. So you have any question on this? Now the magnesium K alpha, aluminum K alpha, as I mentioned to you, these are the laboratory sources. In addition to that, if your spectrometer has helium lamp, one can generate helium-1 radiation which has 20.2 electron volt and the helium-2 40.8 electron volt, precise energies. So if you have helium lamp, one can study valence electrons also, valence electrons of the solid. Okay. So any question on this? No questions? Understood everything? For me, it took 20 years to understand. You finished it in 20 minutes, 20 seconds. Huh? Okay, very good. Okay. So this I have taken last night. I was looking at it, how to excite you. I saw this in the internet. I took it. So you can also go and have a look at it. There is a lot of material available in the internet on photo emission. You can go and have a look at that. Even videos also could be available there. So whatever I have explained to you is the one which is given here. Whatever I have given you, it is given in nice with a colorful way. So these are all filled states. One important point here you should remember is there are empty states here. Filled states are the ones where electrons are filled. But in the solids, there are empty states above the filled states. You don't have electrons to fill them. You don't have electrons to fill them, but they are there. They are there here, empty states. Okay. Now, one interesting thing you should remember here is these electrons are filled up to this point. This is nothing but Fermi energy. I'll come back to this again, but this is a Fermi energy. Above that, nothing is there. No electrons are there. Empty states are there. And then suppose you remove electron from here and take it to this point. This is nothing but your what is called vacuum level. That means the electron is taken away from the influence of the surface from where it is ionized. Now it is free. No more influence is there. That is call it as vacuum level. It is imaginary. There is nothing like level to draw. Vacuum level. So the difference between this energy and this energy is nothing but your work function. That work function varies from metal to metal, material to material. Work functions are there for solids, any solid. It can be oxides, sulfides, metal, semiconductors. Work functions are there. Sorry? In general, I am giving, you can say it is an atom. We're looking at one atom in a solid. But if you want to have full solid, I'll show you one more. I'll come back to that. But this is basically some, don't get confused. This is actually, it's a kind of it's a band. Yeah, it is not shown that way. Levels. That is related to, you can call it as atoms. This is a, you can call it as a band. I think I'll show you another picture which makes it a little more clear. Why this was I got interested in this particular slide figure which I picked up from the internet is these empty states can also be probed. What you can do here, you are actually using some h nu, removing the electron and measuring the kinetic energy of that. In this case, you use an electron of a particular energy and then bring it and fill up the empty states. That will give you electron out, the photon out. Here photon in, electron out, but here electron in, photon out. It is, you can say, XPS to the power of -1, inverse photoemission. It is called inverse photoemission. Photoemission is known, but inverse photoemission. Okay, that is another spectroscopy. I will not be talking about that today. That inner spectroscopy, which probes the unoccupied orbitals or empty bands in the case of solid. For example, some of the molecules, if you see carbon dioxide, carbon monoxide molecule, there is a 2 pi molecular orbital which is unoccupied. So we can actually measure you can actually probe the 2 pi orbital of carbon monoxide using this inverse photoemission. That is another story. Okay, all right. So this is called photoemission spectroscopy, inverse photoemission spectroscopy. Okay. Why we are interested in core electrons? We are interested in valence electrons also. Not that we are not interested in. What is important is electron near the Fermi level is far from the nucleus. If you see here in this particular slide, electron, if the electron is sitting here, core is somewhere here. It is far from the nucleus. Far from the nucleus, right? So it is moving in all directions over the place and will not carry information about any single atom. What does that mean? You take a solid, a metallic solid, metallic bond. How do you describe metallic bond? It's a metallic bond is, where you have a sea of electrons where the ions are sitting inside. Sea of electrons, right? Okay. Now that means the electrons which are moving around in the band, they don't belong to any particular atom. They are not. They are delocalized completely. They don't belong to any particular atom. These are valence electrons. They form valence band or the band which is close to Fermi level. Right? Now, if you look at those electrons, analyze those electrons, you will not be able to say anything about the atomic properties. Okay. So that's the reason why you need core electrons, analyze core electrons. So Fermi level is the highest energy level occupied by an electron in the neutral solid at absolute zero temperature. As you see, you keep filling the electrons and then you reach a place, energy level where the electrons are full up to that point. Now you take the solid to 0 Kelvin, that is the highest level that electrons will occupy. So that is defined as Fermi level, EF. EF. The binding energy is calculated with respect to the Fermi level. Now, Fermi level is something which from there you calculate the binding energy. Fermi level is something, suppose you wanted to measure the height of a tree. There are 2-3 trees, you want to measure the height. What will you do? You just measure with respect to the ground. What is the height? Right? We don't go dig into that and then go to the end of the root and measure it, right? We don't do that. We only do from the ground as a reference. From there you see this is the height. Similarly, you can take it as EF as a common level, EF. From there you measure the binding energy of the electrons which are sitting in the orbitals. Okay, all right. So that is the way that you avoid the work functions, etc. We can avoid. Otherwise, you'll have to do work function measurement and all that. The core electrons are local, close to the nucleus, and having binding energies characteristics of a particular element. This is important. Whereas valence electrons move around, they don't belong to a particular element. I'm referring to metals. I'm referring to metals. Where a core electron is it belongs to a particular element. Core electron belongs to a particular element. If it is a core electron, it is going to sit only in that particular orbital. It's not going to be shared by somebody other element at all. So if you catch that core electron, then you will know something about that particular element. It carries the information about that particular element. So you need to have core electrons. Okay. Now the core electrons have higher probability of matching the energies of the aluminum K alpha, magnesium K alpha. That's what it means. If you use the aluminum K alpha, magnesium K alpha, you remove the core electrons. So they belong to the particular element. Okay. So that is that's why we are interested in core electrons also. So how does this XPS work? So you need to have a X-ray beam of a particular energy, monoenergetic X-ray beam. That H nu is well defined. That I said magnesium K alpha, aluminum K alpha. These two. They penetrate about a micrometer on the surface. They will not go into the bulk. Unlike X-ray diffraction, where it penetrates into the sample, deep into the sample, right? And get diffracted. But in this case, they only see up to about 100 angstroms. I mean, they go up to about a micrometer level. Even they go up to micrometer level, but the information that you get is only 100 angstroms. Remember that. They go inside. They are ionized, but those electrons will not be able to come out to measure the kinetic energy. But you get only electrons which are actually about 100 angstroms. Electrons are the ones which will come out clean, so that you can measure the kinetic energy and get the spectrum. So XPS spectrum contains information only about top 10 to 100 angstroms. X-rays will have 100 angstroms. 10 angstroms is usually, if you are measuring ultraviolet photon spectroscopy, you get only 10 angstroms information. Okay. You need, since electrons are coming out from the solid, these electrons have certain kinetic energy. If you want to measure this kinetic energy, you should ensure these electrons will not collide with anything else before you measure the kinetic energy. For that, you need vacuum. That means low pressure. You need high vacuum, ultra high vacuum environment to eliminate excessive surface. Of course, contamination is another one, but even measurement also you require kinetic the vacuum. The other one is surface contamination. Since you are only talking about analysis of the surface of 100 angstroms, suppose if there is some contamination on the surface, then you will not be able to see the sample properly. You will not be able to analyze the sample. You need to have a clean sample. Because these are the analyzers Spectrum is plotted by computer from the analyzer signal. Binding energies can be determined from the peak positions and the elements present in the sample identified. I'll come back to that a little later as we go on. That is a general way of how XPS works. Any question? No? Let it be interactive. I appreciate if somebody asks questions. No. Okay. Yeah. There are some terminologies, if you go to the literature, there are some terminologies you will see. Photoemission is an analytical tool. And then let us say you have an oxygen atom, you use X-ray photon, it is going to go and knock out 1s electron from that. Oxygen O1s photo ejected electron. Okay. You have 1s, 2s, 2p orbitals. If you see, these are the electrons which are present in the oxygen atom. Okay. So if you remove electron from the core, you call it X-ray photoelectron spectroscopy. This is also usually some, in the olden days, people used to call it electron spectroscopy for chemical analysis. Electron spectroscopy for chemical analysis. You will see in the literature sometimes ESCA is nothing but photoemission spectroscopy. So UPS means ultraviolet photoelectron spectroscopy, ultraviolet radiation is used. Photoemission spectroscopy is also, it means can be XPS or UPS also. So all these terminologies are there in the literature. What is photoemission spectroscopy? What is ultraviolet photoelectron spectroscopy? What is X-ray photoelectron spectroscopy? What is ESCA? All are essentially similar acronyms used here. So in this case, you can actually say for general photoemission has 3 steps: absorption and ionization of the atom in the initial state effects, and then response of the atom and creation of photoelectron, final state effects, transportation of electron to the surface and escape into the vacuum. So this is basically referring to the atom sitting in the solid. Okay. Yeah. Now let's come to here again. Energy levels. Since we have been talking about energy levels, as earlier I showed you, these are all core electrons. As you keep going up, let us take this as a metallic sample. Core electrons are very precise in the atoms. But as you keep coming to the higher level, valence level, you start seeing the bands here, band structure. You are all familiar with the band structure? How many of you are familiar with the band structure? Yeah. So you have these valence levels, right? If you have 2 atoms coming together, they form bonding and anti-bonding orbitals. Suppose you have n atoms coming together, you have a bond, you have a bands forming there, right? So the valence electrons tend to give you bands like this. That is the simple way of explaining. So this is a Fermi level. From Fermi level to the vacuum level, as I mentioned, is the phi work function. Okay. Fermi level is actually precisely defined. We are just saying that, but precisely defined as at absolute 0 Kelvin, electrons fill from the lowest energy states up. When the electrons occupy up to this level, the neutral solid is in its ground state. So you start filling up here, and then almost all electrons fill up to this point, and that is the 0 Kelvin. This is in the ground state. That is in the ground state. The solid is in the ground state. But we are not sitting at 0 Kelvin. Are we sitting in 0 Kelvin? So we are sitting at what temperature? In Kelvin, you should say. About 300 Kelvin, right? So that means at 300 Kelvin, this may not be very precise, but it will be diffused a little bit, but that is still okay. Okay. Now Fermi level corresponds to 0 binding energy. You remove any electron from here, you can take that as zero binding energy. That is the reference point, as I mentioned to you. That is the reference point. Okay. Therefore, Fermi level represents the relative energy of the ion remaining after electron emission, or otherwise binding energy of the electron. Okay. That is because the conduction band and valence band, they separate, whereas in metals, they merge, right? So when they separate, the Fermi level has to be defined in a different way. No, this is for related to metal. Metal semiconductors are different. They have a different band structure, right? Their Fermi level is defined as energy level. If it is intrinsic semiconductor, the EF is exactly at the half the way of the valence band and conduction band. That is the definition of the semiconductor. The definitions are different. Okay. Whereas in this case, there is no valence band and conduction band. They merge. So you have only one EF. There is nothing in between. There is no gap at all. That's why you take that EF as on the top of the Fermi level here. Top of the conduction band. There is only conduction band. There is no valence band here. Only conduction band. Okay. Now, photon absorption in photo emission is very, very fast. It just happens at 10 to the power of 16, minus 16 seconds. It's very, very quick. Okay. All right. So no photo emission for HNU less than work function. Do you agree with this? If any of this statement is we don't agree, you should tell me. Or if you agree also, you can tell me. Okay, this one, first one. Do we agree or do we not agree? You can disagree also, no problem. How many of you disagree? How many of you agree? Okay. Some agree. So those who do not raise their hands for both, they take them as disagreement. Is that right? This is nothing but photoelectric effect, based on photoelectric effect. No photo emission from levels with binding energy Be plus Phi is greater than HNu. Agreed or not agreed? This is how the questions will come. Okay. Kinetic energy of the photoelectron increases as binding energy decreases. Is that correct? I have given you some wrong answers also here. Third statement, is it correct? How many of you say yes? How many of you say no? Yes, raise your hands. No. Both you don't, huh? You both seem to be teachers, so you should allow them to answer. Huh? How many of you agree? Huh? Remember that HNu is equal to kinetic energy plus binding energy. Right? Based on that, you can answer that. Okay. Now, intensity of photo emission is proportional to intensity of the photons. Agree or not agree? Huh? Now, obviously, if you have more photons, it ionize more atoms, the intensity should increase. Right? Now, requires monochromatic incident photon beam. Otherwise, you will not be able to measure the kinetic. You will have a variety of kinetic energies. You want to have a precise one. The range of kinetic energies can be produced if valence band is broad. Is that correct? Valence band is not a well-defined energy level. It's a broad one. So you'll have a broad photo emission spectrum. You'll have all kinetic energies. You'll have all kinetic energies. Each element has unique set of core levels. Agreed or not? Hello, the last two, you both should come and sit here. You want me to focus? Laser will come there. See that man, that head and these two heads. This laser is a beautiful instrument. When we were doing our masters, my teacher taught us the laser action, the chemistry of laser action. That was in 1980s. Today you have laser here. So we were excited. What is this laser and all that at that time? What is the acronym of laser? All of you know that? Now go to IIT Madras. Now laser shows are going on there. All right. So therefore, kinetic energies or binding energies can be used to fingerprint the element. If you know the binding energy of a particular electron, you can figure out the element from it where it is coming. That is how elemental analysis is possible using XPS. Okay, all right. That is kind of a summary I wanted to give you. So binding energy represents the strength of the interaction between the electron. Electron has these quantum numbers. What are these quantum numbers? N, L, M, S. What are those? Teachers. Non-teachers or students. So a particular electron, we have 4 quantum numbers, right? And then, so it depends on the interaction between the electron and the nuclear charge. The binding energy is directly related to that. Higher the N, higher the binding energy. So on and so forth, right? So in gases, binding energy is nothing but ionization potential, simple. No work function there. Binding energy of 1s electron is greater than binding energy of 2s electron is greater than binding energy of 2p electron, binding energy of 3s electron, and so on. Is this statement correct? I am not allowed to examine you, I think. Otherwise, I will put a question paper to you. Pass or not? Is this correct statement? Right? Similarly, nitrogen 1s, magnesium 1s, aluminum 1s. This is less than this, that is less than that, that is less than that. Is that also correct? Why it is correct? Why this is correct first to the second one? Why second one, third one is also correct? Why is it? Sir, it is very easy to operate cell phone, sir. Don't ask me these questions. Are you talking about this? This one. What is the difference? Atomic number. She is saying something. Size increases. Okay. Yeah. So actually, nuclear charge increases here. Same 1s electron, nuclear charge increases. Right? See nuclear charge here. Are you seeing it? And here, orbitals are different. L is different, M is different. Right? So they are actually going far away from the nucleus. Right? So the influence of nucleus is less. So nuclear charge influence is less. Okay? Okay, good, very good. Now, binding energy of orbitals is not affected by isotopes. Suppose isotope carbon 12 and carbon 13 will have the same binding energy. What is carbon 12, carbon 13? What are isotopes? Right. Okay. But which is NMR active? This one or this one? Anyone taught you NMR? Who taught you NMR? Okay. Okay, so carbon 13 is the active one, right? Okay, so this is how a spectrometer looks like. Right? So you will have a sample holder here, a specimen sample, small piece of specimen sample, and then you have this light source here, X-ray, and then this is the operating thing for X-ray, and then the X-ray falls here, electrons will come out, these electrons pass through this analyzer, this is the analyzer, okay, and then this entire setup in this box is kept in the vacuum chamber. This is all vacuum chamber, UHV chamber. Ultra vacuum is created by turbomolecular pump, and then backup pumps. These are the pumps which create vacuum, that is low pressure. Okay, so that is a separate technology that is called vacuum technology. That is very well established, vacuum technology. So that we use this, these people use this to build spectrometers. Okay. All right. So let me go to the next one. Okay. So here I gave the same experiment in a different way. For example, here these are the this is a metal. Your core electrons, core levels, very well localized core levels, and then you have, as you keep going, valence band, conduction band, etc. Right? This is the energy increases. Energy increases. Binding energy also increases this way. Binding energy is opposite. Okay. Now you use this these electrons here. So you can analyze this this thing. I think I will skip this one a little bit better. I don't know whether you are interested in, but these are the some of the details of the X-ray tubes. X-ray tube has structure like this, but what is important is at the tip here, if you see here, this tip, it's like this. One side magnesium, other side aluminum coated. And then these are the filaments. There are filaments here. These filaments, you apply voltage, and these voltage filaments eject electrons. These electrons go and bombard here, and as a result, X-ray comes out. So you can switch. You want X-ray, aluminum K alpha X-ray or magnesium K alpha X-ray. You can switch manually. You can switch that in the spectrometer. Okay. These some details of the. The important thing is this is the one I see here, aluminum and magnesium, the tip. So the filament here, the filament gives electrons. These electrons will bombard aluminum to get X-rays of particular energy. What I give you, magnesium K alpha or aluminum K alpha will come out through this window. Very hot. So you have to have cooling water, otherwise it will melt. X-ray tube can melt. So regular cooling water should be there. So this is the cooling water. This goes in and then comes out from the other side. This is in, this is out. That's very important. Otherwise, if the cooling water shuts off, the X-ray shuts off. Okay. These are lab experiments. We are talking about laboratory potential experiments. All right. I think so. The what we are looking at is K alpha. You are talking about. This is alpha. This is beta. So this is the radiation which has a very precise energy. This one alpha, K alpha. So this is the X-ray spectrum of aluminum K alpha or copper K alpha. This is the characteristic. But when you are actually bombarding it here, what you get is this kind of spectrum. What we are looking at is this one, alpha. That alpha is the one. This X-ray notation is there, alpha, Y alpha and alpha 1, alpha 2. The electrons are coming from P3/2 to 1s, that is alpha 1, and from here it comes to 1s, that is alpha 2, right? So this is the X-ray notation, KLL, this is the K shell, that is 1s, this is L shell 2s, and L2, L3, 2P. This is X-ray notation. What you are seeing is this X-ray notation. This is what we are familiar with. Okay. So if you go to ozone spectroscopy, you see this notation. KLL, LMM, they use that kind of a notation. That is X-ray notation basically. Okay. Okay, so these are all again the X-ray tube, etc. As I showed you here, aluminum, magnesium. Okay. This is how it looks like, X-ray tube. And then you generally people use only these two. But sometimes people go even zirconium and silver also. But that's very rare. That's only for a specific thing. The energy is very high here. So width is also very good here. The X-ray width is very good. If the width is very small, the resolution is better. The width is X-ray width is small, resolution is going to be better. Whereas here width is very large, so resolution may not be very good, of course, but you can get deeper levels also. X-ray XPS can also be carried out using high energy synchrotron facilities. Synchrotron radiation. How many of you have heard of synchrotron radiation? Anyone? Synchrotron radiation? Any physics student? How many are physics student? Chemistry? Biology? Engineering? Okay. Data science? Computer science? Nobody is there. Very good. I am very happy. Okay. Synchrotron radiation is basically, I hope I have some, we have that in India in Indore. In Indore. It's a very good facility. Government of India has established that. Thanks to Government of India. Go look at the website. Some of you can use it if you are doing your research. You can use it. They give you, I think, the nice accommodation there. You want to have an analysis, you can write to them. They will probably give you transportation also, the travel also. They give you accommodation there. You can go and do experiment. All those facilities are available there. Okay, they help you a lot, but use that. This is a nice radiation center. They have good facilities there. Okay. So what this does is, in synchrotron radiation, I don't know, I keep on talking, and I can talk till lunch or even till evening also like this. Huh? But the organizers have to allow me, no? We'll just take a few minutes break. I have to take tablets. I'm an old man, no? Not that old, but you have some water, please. Don't record all this, huh? It's going live. Oh, then I'll go this side. Water is there. Yeah, I don't mind. ఎంత ఎంత టైం మాట్లాడాలి మీరు? ఇంకా నాకు గంట పడుతుంది ఇక అయ్యే
సార్ మీరు బ్రేక్ స్నాక్స్ తిని మీరు ఒక హాఫ్ అన్ అవర్
spectrum of energy all the way, you know, very intense, log intensity is very high intensity, and then different energies also. So you can choose wherever you want. In the case of lab experiments, you have only magnesium alpha, aluminum K alpha. But in this case, you can choose any energy you want. You want to have 100 electron volts, 200 electron volts, 500 electron volts, 1500 electron volts, 2000 electron volts. You can choose whatever you want, and the beam intensity is very high. That's why you get a spectral quality is very good. But this is done in the synchronous radiation centers. We have it in indoor. Kolkata is a small one. Yeah. Okay. So this is the one. Raja Ramana Center for Advanced Technology indoor. This is a website. All of you should go and look into that. Okay. So here, these are the laboratory photons. But here, you know, you'll get anything other than this also you can get here. Okay. So this is how it looks like. This is the ring actually, where electrons are circulated here. And then there is a bending magnets, you know, these are wigglers and undulators, they call it. Physics students will know better these things. So then wherever there is a bending magnet, there is a radiation coming out here. There is a radiation coming out. These are all radiation. So these are called beam lines. People call it beam lines, where you can set up your experiment, XPS, XRD, infrared, so many other experiments can be set up there, and then you can do the experiment. Okay. So this is how it looks like. So this is the Raja Ramana Center for Advanced Advanced Technology. Government of India, Department of Atomic Energy has established this. So this is the link. Please have a look at those links. That will be very useful. As students, you should know that. Okay, so quickly, this is how it is. Any X-ray machine experiment would require these things: electron energy analyzer, X-ray source, argon ion gun to clean the surface, and then neutralizer. When you remove electrons, the surface gets charged. So you have to neutralize it. Otherwise, you will get a wrong result. So that is neutralizers is important. Vacuum system, electronic controls, computer system, etc. And then vacuum is of the order of -7 Pascal. It is even now these days you get it much better than that. I know I told you the reason why you need vacuum. Electron should not lose its energy, kinetic energy, before it is measured. You need to have enough free path so that the electron can travel to the detector. So that's the reason why you need to have vacuum system. Okay. And then of course you have all these things here. So this is how it looks like. So this is the sample, and then you have a HNU coming out here, and the electrons are coming out. These electrons pass through this, and then pass through the analyzer and goes to the detector. So the detector detects how many electrons are coming, and this analyzer analyzes the kinetic energy. So this many electrons are coming out with this particular kinetic energy. That's what you get the spectrum. You get the spectrum. This is nothing but, you know, you have a positive charge applied here, negative charge. This is a kind of a concentric cylindrical analyzer. So through this, electrons move around. It goes from one end to other end to the detector. Okay. All right. So this is how it looks like. These are different types of analyzers. We will not worry much about those things. This I have already shown you. So this is a spectrometer. This is a spectrometer which I worked in 1984 to 1990. I did my PhD on this machine, so I like this machine. I used to sleep with that machine. I used to clean it. So the 24 hours I was with this machine. It gave me PhD thesis. Okay. So it looks very complicated, but this was the machine which was built in 1980s. It was available, and like this, there are about 4 or 5 machines in India at that time. And then there is a book in which, you know, they have put a map of India, and they said India has XPS machines. But today in every street there is one XPS machine. Okay. All right. This is a modern machine. I think I have to take a photograph of machine here after this talk. Here, please take me there. I want to take a photograph. So this is a machine which was installed in 2022 ARCI. There's one machine. There's one here. I think in Chennai itself, I'm sure at least about a dozen machines are there. And IIT has 3 machines, 3 or 4 machines, IIT. Okay, this is how it looks like. But the difference between this, there is one more I want you to, this is another, this is also XPS machine. This is built for experimental XPS machine in National Chemical Laboratory. This costed about 5 crores. It was built, custom built electron spectrometer where you can do experiment the way you want. Whereas the previous one, these are all, the previous one is a commercial machine, a thermoscientific. And this one is, I don't remember, this machine is from UK. I don't remember the name of that. Okay. All right. So if you want to read something about this machine, Journal of Physical Chemistry C, 2013, volume 117, this one, this you can go read that. Okay, it is published there. Okay, I already explained this. I will skip this one. So when you have created a core hole, so this excited atom, after creating a core hole, that means you remove electron, it has 2 ways of decaying. You know, this is a high energy system now. It decays by releasing the X-ray or by releasing OJ. That's the OJ electron which I explained to you, right? So this is the one that gives you another. This is a non-radiative decay. This is a radiative decay. These are the 2 decay processes that photoexcited atoms undergo. But one interesting thing is, the atomic number is low, for example, less than 15 atomic number, you get X-ray yield is very low, but you got mostly OJ electrons come out. That's the reason why OJ spectroscopy is very popular for analyzing oxygen, carbon. This is low atomic number elements. But as you keep going to the higher level, higher atomic number, the OJ intensity comes down, X-ray yield goes up. X-ray fluorescence comes up, is more for a higher atomic level, atomic number elements. Okay, so that is something which is a kind of experimental thing that is established. Okay, coming to this this one, you have this. This is the molecular the energy density, electron density states of a material, where you have valence band, core levels are here. The valence band is a band, it's not a level, it's a band. So this is how it looks like, and this is the EF, that is the highest you know, energy level that is occupied by the electrons in the solid. And then you have vacuum level somewhere here. Vacuum level, I said, you know, it is the electron which goes to that level where it has no influence from the core, the hole that is created in the solid. So this energy difference is nothing but your work function, right? So this is the this scale is density of states. Physics students understand this better than chemistry, biology. Density of states. So density of states are this side, and this is the energy. Now, if you try to map this using the spectrum, photoemission spectrum, you get this one. So these 2 levels will give you the 2 peaks here. This band will give you a band like this. This is the valence band. So your photoemission spectrum exactly maps the electronic structure of the material. This is how it looks like. Okay, do you see? These 2 levels will give you peaks here. See the difference here. This is fairly well defined, whereas this is broad. Did you notice that? What is the reason for that? Spectral width depends on the resolution of the spectrometer, depends on the line width of the radiation, so on and so forth. Right? So that's the reason why you get this one. Okay, you are also familiar with this spectral line widths. Have you studied spectral line widths? Spectral resolution, spectral line widths. Some of you, if you want to know, read Banwell textbook, Banwell by Spectroscopy Manual. Read that book. Okay. So typically, this is how it looks like. As I mentioned to you earlier, also these are the energy levels. You get these peaks here corresponding to these, and this is the band here. that is a work function, this is a vacuum level. This is the what is you should get in the photo emission spectrum. This is a real sample and this is the spectrum. Now this EF is taken as 0 Fermi level. So in the real spectroscope spectrum, that EF, wherever that EF comes, that is taken as 0. That is taken as 0 in the spectrum. So you get the 5D. For example, in this case, let's say one of the elements like gold, you have 5D, 5P, 3 by 2, 5P half, 5S, 4F, 4D, 4P, so on and so forth. So n is equal to 4 and 5 orbitals or levels are probed here. You don't need to go deep further. N is equal to 3, 2, you don't need, because this is enough to get information about the sample and then the elements present in the sample. Okay. So you get this kind of lines here. Notice here 5D, 5P, there are doublets here. You see there's a doublet here. 5P2, there 5D2, 5S there is no doublet. 4F there are doublets. 4D, 5 by 2, this is also 4D. This is wrong, I think. 4D, 5. 4P and 4P, this is 4D. This is not 5, this is 4. So there are doublets are there. Notice those doublets. This I think I have covered it. So this is something about vacuum technology. I think I will skip this one because I don't have much time now. Okay, now coming here, this is a solid. This is a material where you are doing the experiment. So these are the atomic layers, top atomic layers, and then you have this X-rays coming out. These solid lines are X-rays coming out, and these dotted arrows are basically the electrons coming from the atomic layers. So these lines, that you are seeing from this light blue, these are the ones which are coming out after ionization from the particular atom. These are all coming out. Whereas there are the deeper levels, atomic layers deep inside are also ionized, because ionization depth is about 1 micrometer, right? So when they come out from here, but they are actually now, during their path, they start interacting with other cores, right? So that means they are losing some energy here by interacting with these surrounding atoms or surrounding charge density there. They lose some energy. As a result, by the time they come out, these are the ones you see, this one, this one, this one. They lose a lot of energy. They come with a lower kinetic energy than actual kinetic energy, right? So they form background in the spectrum. They form background in the spectrum. So what is important here is just to say outer surface, inner surface. These inner surface electrons which are also coming out, but they don't give you clean spectrum. They give you background. Whereas the electrons which are coming in the top layers, 1 or 2, 3 layers, they are the ones which contribute to the correct spectrum, which actually reflect the elements present in the sample. I think I skipped this one. Let me go to the spectral interpretation. Now here, so this is how the spectrum looks like, photo emission spectrum. So this is the EF, that we take it as 0. Okay, the binding energy keeps increasing in this direction, where the kinetic energy should be opposite, correct? So it is going in opposite direction. So you get a lot of peaks here. For example, 2P, 2S, the Auger peaks also appear here. As I mentioned, the Auger peaks also appear in the spectrum. You need to distinguish that. You should not interpret this as a XPS spectrum. You should be able to distinguish that is Auger spectrum. There are ways of doing that, and you can see there is no background here, but here there is some background, and here lot of background, here lot of background. The background keeps on increasing step by step. These are the ones which are coming from the secondary electrons, which I told you they are coming from the deeper layers. But then by the time they come, they lose their energy, so they come at a higher binding energy or kinetic energy. Lower kinetic energy, higher binding energy. This is lower kinetic energy, higher binding energy, this region. That is how the background builds up there. The background builds up there. All right. Yeah, just to quickly So the kinetic energy increases from left to right, and then binding energy increases from right to left. So this is a kind of a 1000-volt scan. You know, you go to any operator, XPS operator, he will say first he will take 1000-volt scan, and then he will go to the particular peak. You know, if you want this peak, you analyze only this peak. You want to analyze this peak, you analyze only this region. Okay, so that's the basically typical 1000-volt scan. Okay, so let me show you this one here. Spectral interpretation again. Now, as I mentioned to you, the background keeps on increasing. The reason I told you, these are all inelastic scattering processes where they reduce the kinetic energy and prevent the escape from the surface. They don't escape from the surface without losing energy. That is the reason why they form the background here. Okay. Now you see 4F, gold 4F. For example, this is a gold spectrum 79, atomic number 79. This is recorded using magnesium K alpha radiation. Magnesium K alpha radiation. Okay. So you have a doublet here. You see there are two lines here, but both are 4F. But one is 4F 7/2 and the other one is 4F 5/2. 7/2 and 5/2. And here 4D. Both are 4D, gold 4D. But here this is 5/2. This is 3/2. There are doublets happening here. This is a doublet. This is a doublet. And P also is a doublet, but one S for S orbital doesn't have a doublet; it is a single line. So that is something which we need to now understand. Okay, I'll just skip this. Yeah, why these doublets? See, for example, you know, P, D, F peaks, 2 peaks are observed. P, D, F. PDF L values, no? L is equal to, for P, L value, what is the L value? Yes, for S orbital, what is the L value? So, L values are different here. Can be any N value, but L values are different. Now you see all these these will have 2 peaks here. So this separation, this is because of what is the phenomenon called spin orbit splitting. Spin orbit splitting, right? So because of spin orbit splitting, you get 2 peaks, and you with a notation 4D 5/2 and 4D 3/2. Let's see how you get this 5/2 and 3/2. There seem to be there is a area ratios are also fixed here. Area ratios are also fixed. This is the reason why it happens. For example, take one orbital, we have 2 electrons, which are one is spin up and spin down, total S is equal to 0. Okay. Remove any one of those electrons. So, for example, remove this electron, so you get spin up state. Now, this is initial state, this is the final state. There is no spin orbit interaction here. Only spin is up. No interaction between the orbital quantum number. Okay, so now, but this electron is sitting in a, let us say, p orbital, and p orbital has L is equal to 1. Spin here is plus of or minus of. So the spin and orbital interaction takes place. L plus S or L minus S, 2 states will come. L plus S is equal to L plus of, L minus of. That is 1 plus of, 1 minus of. You get 3/2 and 2/2. So 2 states, final states will come. That is the reason why you get doublets in P, D, and F. Okay. So here that's why P 3/2. So this will have a degeneracy. Degeneracy is given by 2J plus 1. This is a J orbital, J quantum number, which is a combination of L plus S. L is equal to 1, S is equal to plus minus half. So if S is equal to minus half, you get 1 minus half. Otherwise, you get 1 plus half. That gives you 3/2 and half. Okay. The degeneracy, what is degeneracy? What is the meaning of degeneracy? You can have 2 states but same energy. For example, in quantum mechanics, if you take quantum mechanics, they will give us 2 different wave functions for same energy, right? So that is a degeneracy. So these states have degeneracy. So degeneracy is given by 2J plus 1. J is your quantum number here. So if 3/2 into 3/2 plus 1, that is 1 degeneracy. 2 into half plus 1, that is another degeneracy. That will give you P by 2 and half. So that is how you get the difference here, and energy difference as well as intensity difference. Okay, this is because of the spin orbit coupling. So you can see here, this is the p orbital. For example, I just showed you here. For example, this is a p orbital, silicon 2p core level. You see there are two peaks here, p3 by 2, p half. Energy difference is there, and as well as the intensity, the energy intensity difference is also there. So you calculate this one, the ratio of the 2p potential signal, any 2p of any element you take. So you should get intensity 2p3 by 2, intensity 2p half. The ratio of the intensity of the two peaks, doublets, is equal to 2 into 3 by 2 plus 1, 2 into 1 by 2 plus 1. The intensity ratio should be 2. That is 3 by 2 to half. The ratio should be 2. Any p orbital you take, it should be 2. That means, you calculate the area intensity, and then divide it, you should get 2. 3 by 2 by 1 by 2. If it is the other way around, it is half. Okay, that's what is given here. So this is the intensity of 3 by 2, and this is the intensity of half. The ratio of these two should be equal to 1. So you draw a line here and see get the value, and then you should get 2. Not exactly, plus minus small point, but okay. So similarly, p orbital I have given you. D also, dl is equal to 2, and d will have L minus s and L plus s. If you take the J quantum number is going to be 3 by 2 and 5 by 2. So you get the area ratio 2:3 and area ratio 3:4 for L is equal to 3 f orbital. So all of you should do that exercise by yourself. You are doing like this, note down and then see whether those numbers are correct or not. Students, where is your pen and pencil? Huh? Pen, pencil, paper, nothing. Huh? Okay, he is coming, I think, to ask me to stop, looks like. So point to remember, for PDF peaks, doublet peaks are observed. For say S electron, no doublet peak observed. Why? L is equal to 0, right? L is equal to 0, so there is no doublet. Suppression is due to spin orbit splitting. The values of spin orbit splitting of a core level of an element in a different compounds are nearly same. Same element, you can put it in any compound. For example, silicon, any compound you take, the difference is going to be same. Okay, and then the level with highest J value has the lowest energy. Okay, this is basically based on Hund's rule. If you understand Hund's rule, you can understand. Otherwise, right now, don't worry about it. But it is based on Hund's rule. Okay, so now you see here, spin orbit splitting of copper 2p photo emission. So you get 2p3 by 2, 2p half. Energy difference is about 19.8 electron volt. Peak area 1, 2, 1:2 ratio. That's what we said, right? So L is equal to 1, S is equal to plus minus half, J is equal to L minus 1, L plus 1, so half and 3 by 2. This is the interpretation of p orbital. If it is a d orbital, L is equal to 2. Okay. If it is f orbital, L is equal to 3, and so on and so forth. So you do that exercise by yourself at home. So this is a d orbital. Silver 3D. This is silver 3D photo emission spectrum, and then this is gold 4F spectrum. Here L is equal to 3. I have taken it. S is going to be say plus minus half. L is equal to 3. So you get 5 by 2 and 7 by 2 here. Okay. I have seen in papers, in thesis, which come from different universities. You know what they do? They just put the 7 by 2 here and 5 by 2 there. They go record XPS spectrum, and then the interpretations are terrible. You ask them what is 7 by 2, what is 5 by 2, how do you get it? They don't know, and they reverse it also. Unfortunately, I see them published in journals. Some journals I see, oh, this is wrong. The reviewers don't see that properly. Otherwise, they will point out. But right, so you should learn some basic reasonable. See, X-ray spectroscopy is not so straightforward. But whatever is standard one, you should know that. Right? Standard fundamentals you should know thoroughly. Okay, so there is something called, there is a gentleman called Koopman. What he said is that the binding energy of the electron is equal to energy of the final state minus the energy of the initial state. That is correct. But that is also not correct, because there is something called relaxation effects. There is something called relaxation. If there is no relaxation, this is correct. If there is a relaxation, certain relaxation, for example, the excited atom relaxes, then that is not true. That is not true. So that relaxation energy has to be taken into account. Okay, that is called Koopman theorem, but we generally don't worry about it. That is worry about the theoreticians who do all this, they break their head into the Koopman's theorem. So we will not worry much about it. Okay, but there is something that's a very interesting observation made by Koopman. What he said was, you see here, there is a straight line here. This is the experimental binding energy. This is the calculated binding energy by theoreticians. There is a nice correlation here. You see here, it starts from 305 to 90. What is the difference? 15 electron volts. That 15 electron volts continues this side and this side also. That is the relaxation term that has to be taken into account if you are doing theoretical work. We will not worry about it. Okay. Okay. Now complication starts from here. Now the question here is that if you have a core hole, there are electrons here. These electrons also, they will not keep quiet. You remove a core hole, these electrons will not keep quiet. They will start because it's an excited atom. So this electron will go up because of the to relax the atom. This will go up from here to there, taking some energy. This is called shake-up satellite. And this one, this electron can even come out of the atom also. Along with this, one more electron which is sitting in the valence level can actually drop off. That will give you satellites. I think all those distribution of paper should be done later. They are not paying attention here. Okay. So this leads to shake up and shake off satellites. This will become a, you can start seeing that. For example, I will give you one quick example: copper sulfate, copper oxide, and copper metal. You see the photoemission spectrum difference. You see this? All are copper 2p spectrum. This is copper 2p spectrum. You understand? Copper 2p spectrum. That region is taken. Copper 2p metal has beautiful two peaks. One here, 3/2 half. We know that it is because of spin orbit splitting. Hello. Then, when you have copper 0, copper oxide, what is the oxidation state? This is 0, this is 2 plus. This is also 2 plus. When you have 2 plus, you start seeing, some additional peaks here. These are nothing but satellite peaks, which is the origin of that I told you in the previous slide. Copper is a beautiful example for that. Copper is a beautiful example. There are much more complex things. Copper, for example, cerium 4 plus has a very complex satellite spectrum. And then in addition to that, another complication is multiplet splitting. This is called multiplet splitting. So you remove a core electron, and there are unpaired electrons here. This unpaired electron, these unpaired electrons, they interact. They give you various multiple states. There are several final states possible here. For example, this remove one electron here, you get a spin up and spin down. This gives you one final state S7. This gives you final state S5. These are nothing but term symbols. Some of you may know term symbols. So two different final states. That makes the life more difficult. In the spectral interpretation, it becomes a little more difficult. But the origin is multiplet splitting. All right. This is another important concept: chemical state identification, inspection of bonding environment. Now, this is all of you. Hello. All of you pay attention here. Now here, this is a very interesting thing where you have this molecule. This molecule is called ethyl trifluoroacetate. Ethyl trifluoroacetate. Okay, this is acetate group, ethyl trifluoroacetate. Now it has 4 carbons. Typically, if you record carbon 1s peak, 1s spectrum, you should get a single peak, but you are getting 4 peaks. You are getting, the spectrum gives you 4 peaks. That means it has 4 carbons for 4 different carbons. 4 carbons it is there, we know that from the formula, but spectrum says 4 different 4 carbons. Carbon is carbon, but 4 different carbons. The thing here is that the chemical state, you see carbon here and this carbon and this carbon, this carbon, surrounding is different. You see that surrounding here? See here, this carbon is surrounded by fluorines and then CO group. What is a fluorine? Fluorine is has a negative inductive effect. Chemistry students understand that negative inductive effect. It withdraws electrons from the carbon. So as a result, what happens? The carbon delta positive will increase. It has higher delta positive. If it is higher delta positive, 1s electron, if you want to remove, you need to spend more energy, right? So the binding energy is going to be more. It is strongly bound because it has a positive charge, right? So as a result, binding energy is more, kinetic energy is less. That's what is given here. You see here, this is the binding energy is increasing from this side to that side. This is a higher binding energy peak, which is related to carbon. Next one is this carbon. This has only surrounding is oxygen, carbon, and oxygen here. And look at this carbon is hydrogen and hydrogen. CH3. CH3 has a positive inductive effect. It contributes to charge here. So this is delta positive is small. This delta positive is very high. As a result, this peak has a higher binding energy, whereas these 2 peaks have lower binding energy. That's how you see 4 different peaks which are related to the 4 carbons. This is called chemical shift, which you must have heard in NMR spectroscopy. That is NMR spectroscopy chemical shift. This is a photoemission spectroscopy chemical shift. So this is a very important thing. People normally people who do these experiments, they look for this only, so that they can interpret photoemission spectra. Some of you wanted to read this. There is a nice article, accounts of chemical research in 1970, but there are nice articles even today, they are available. But old is gold. Read all the old articles because they give details. Older generation is also gold generation, I will tell you. Of course, you are also gold, you are more than gold, but okay, all right. So quickly, just to give you the chemical shift, its effect on oxidation state. For example, take silicon, oxidation state is 0, so it has 99.15 electron volts peak will come. But you take same thing to SiO2, this is oxidation state 4 plus, you see it has gone from 99 to 103. Binding energy has increased by about 4 electron volts. This is what people look for when they record a spectrum. They see the binding energy changes are there and trying to correlate them with oxidation states of the elements. Okay, all right. This is a beautiful experiment. I'll just quickly take a few minutes and finish off. You see this one. This is a platinum metal. This is a 4F spectrum. 4F F electrons, 4F electrons. Now the platinum 2 and platinum 4 complexes here. Are you seeing this? This is a platinum. This is a NMe2. The 2 methyl groups attached to nitrogen. That entire thing is attached to the platinum here. There are 2 NMe2 groups are attached here, 1 chlorine here. And here also there are 3 chlorines here. Only 2 NMe2. There are 2 additional 2 more chlorines attached to this platinum. So these 3 compounds, these 3 if you take, you should be able to identify using photoemission spectroscopy. Now that's what is given here. You see there are 3 chlorines. They withdraw electrons. Delta positive is more in the platinum here. That will have higher binding energy. You can see the binding energy is high compared to this, compared to that. The binding energy is decreasing from here to here to here. Right? That is how people analyze. In organic chemistry, people have analyzed this. This is published in the PCCP 2020. Uh, uh, yeah, I think probably this is correct. Check it. Okay. So inorganic chemistry people like try to look at the oxidation states of different elements present in their complexes. This is an interesting thing. Now I'll take a little bit of quick quiz from you. I have given you this in an examination and ask you to interpret. Tell me what you understand from this. Make any statement. Analysis, Sir, this is the meaning of this, this is the meaning of this. This is actually moon dust collected from moon by one of those satellites which went there, brought them to Earth and then given it to a XPS lab, and they recorded this spectrum and published this in a textbook. I don't remember which textbook I have taken. This is from a textbook material. Now tell me quickly, a few of you, at least one or two, what do you understand from this? This is a photoemission spectrum, XPS of a sample of moon dust. Quickly. What is it? Okay. 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 Not 100% correct, but okay. Any other? I'll go with a disappointed face. I'll tell you. At least one answer should come. Having spent so much of time. Hello? At least physics student should tell. Yeah.
Because the great amount of effort, they collected dust from the moon. So
they brought it here.
So we have to find out.
Right.
What is the content of
that is the analysis they have done. Now you have to make conclusions out of that.
Fine. What is the material? Not basically.
Okay. Somebody is saying something. Who is that? Okay. Yeah, elements which there are some elements, same elements are there on Earth also. Okay. All right. That is one observation. Any other? Surface water. Oxygen. Yeah. So oxygen, carbon, which are there on there also. Here also we have. Okay. Any other students from backbenches? Okay, so this is a question I keep asking everyone. Anyway, the point here is all these elements are present on Earth. The same elements are present in moon also, in moon dust. Earth also, you take the sample and then analyze it, you will get more or less similar, more or less these things can be there. It has silicon. We also have silicon. Marina Beach has so much of silicon. Magnesium, aluminum, calcium, potassium, titanium, sodium, oxygen. Right? What they are looking for, what was missing here in this, why they analyzed it, I think in my opinion, they want to see whether any gold is there. So that, they just bring few tons from moon to Earth and then extract it. That was the idea. But unfortunately, they didn't find any gold there. All right. So, and also you see here magnesium 2p, magnesium 2s. Ionization energies are different. They are very able to identify magnesium 2p and magnesium 2s. Silicon 2p and silicon 2s. Calcium 2p, calcium 2s. Titanium 2p, potassium 2p. Carbon 1s, oxygen 1s show very high intensity. The reason is, generally the reason is for carbon and oxygen, one cross section of ionization cross section is very high. Even if you have a small amount of carbon and oxygen, they really show up. XPS cross section is very, very high for carbon 1s and oxygen 1s. Very small amount, you just get a good signal. Right? But definitely carbon and oxygen are there. Okay? And of course, some more can be done, but I think it will take some time. I will stop here at this, and then I go to the next one. I think this this is one slide I want to quickly tell you. You take this this part here. This is the photo emission spectrum which was recorded somewhere in 1900, 120 years back. They saw two lines here. There was no computer, nothing was there. They only had a photographic plate. When electrons are coming, they expose this to photographic plate. They saw two lines here. They said this is photoelectron spectrum. For them, it was a Nobel Prize winning movement. The same two lines now we are seeing as peaks here today. We are recording on this computer. The interesting thing is, this is a clean gold foil. You see both the peaks are there, gold. It is saying, the spectrum says it is a gold because it has a gold 4F spectrum is there. Same clean gold foil is, you take it and put some dirty finger on that and record the spectrum. These 4F peaks are missing here. Spectrometer says it is not gold, but you know it is gold. So how do you understand? That is the point. How do you understand that? As I said, it can only see up to 100 angstroms. Below that, it doesn't see anything. So that is highlights the importance of surface cleanliness of the sample that you are recording. Okay, it is a clear example of how surface cleanliness is very important. All right. This is another interesting example. I have taken it again from a book actually. I should put the differences here. This is one of this is I've taken from Atkins' book, one of these editions, earlier editions, maybe 5, 6, 7, 7th edition of Atkins. You see here, this is what is this ion? Huh? Not really. Huh? Amma, my ears are not working. Azide, correct. Azide. So azide, what is the electronic structure of azide? Is it like this or is it anything else? So they recorded the spectrum, said they saw two peaks here. The strong peak is because of this is coming at lower binding energy. This is coming at higher binding energy, right? Now this lower binding energy is interpreted as n minus, two n minuses are there, and whereas this higher binding energy is n plus. Obviously, n plus charge will have higher binding energy. So and it is only one nitrogen. So its intensity is half of that. So this is the electronic structure of azide ion. How beautiful it is! You agree or not? You don't enjoy it at all or what? Beautiful interpretation, right? Azide ion. Clear. Two n minuses are there, one n plus is there. And then the other one is sodium, of course. You have sodium plus is there. Sodium plus, n plus. Two positive charges and two negative charges. Sodium azide compound. Is it not beautiful? See, there is no mathematics here. Very simple, nice, beautiful XPS spectrum. That's it. Okay. Okay, I'll keep shifting. This is a research problem. Quickly, I will tell you. They have actually tried to take this porphyrin ring. I don't know how many of you know porphyrin ring. Porphyrin rings are there in our blood, in the trees everywhere. Porphyrin ring. They want to put this cobalt in this. Cobalt forms nice bonds with the porphyrin nitrogens. So naturally it is available, but they synthesize it in the electron spectrometer. So they take this one and then start putting cobalt atoms inside the ring. You see the cobalt atom is going there and sitting there, and then the spectrum keeps on changing. You see that cobalt nitrogen bond is formed here. There is no cobalt nitrogen bond here. There is a cobalt nitrogen bond formed in the porphyrin ring. This is synthesized. This very interesting thing is this is synthesized in the spectrometer, not in your lab using test tube and beakers. This complex is in the spectrometer. You see that beauty of that? So this is published somewhere in JAX to 2006. All right, so I think that more or less covers the XPS part of it. And if I have to give another, I'll need another 1 more hour, I'll stop here. Okay, this is a UPS spectrum, UPS of that. This is something which it will take another. You should give at least 2 hours or 3 hours to me. Otherwise, don't call me coming all the way 20 kilometers. All right. Yeah.
Participants, any questions?
Actually, a teacher will get satisfied if you get a couple of questions. Otherwise, he will go back with, basically you use this, you have this X-ray value, 1486.6 or 1253.6, right? Kinetic energy that is known to you because you are using the beam, X-ray beam in the spectrometer. Then you measure you measure the kinetic energy of the peak. For example, okay, how do I tell you? I will tell you this way. I'll just show you that. Now, for example, if you take this one here, the question is how do you measure the binding energy?
Actually, in the instrumentation part, we get the kinetic energy of
Correct.
the electrons, sir.
So you H nu is equal to the H nu is equal to binding energy plus kinetic energy. That is our great grandfather said that, Einstein. We respect him. And then starting from there, this is the binding energy which you can actually directly measure it. Otherwise, the same thing can be measured using kinetic energy also. Suppose your spectrometer measures kinetic energy, then kinetic energy of the energy of the electron beam, the photon, the H nu minus kinetic energy will give you the binding energy. Okay. Normally, the binding energy directly you get it from the spectrum. If the spectrum is recorded in the binding energy mode, normally they use only binding energy mode. I don't know what are they doing here. It can be measured in kinetic energy mode also. People used to do that earlier. Now everything is in binding energy mode. So you get it directly. But the question is whether this binding energy is measured correctly or not, that has to be taken into account. Because there is a reference point, carbon 1s, 284 electron volt. That has to be recorded. With respect to that, you have to interpret that.
Okay, sir. Got it.
Yeah. Any other? Yeah, they both are discussing to ask questions or ask, no problem. No. See, this is something which I started with. I must also thank my teacher, Professor D.K. Chakraborty from IIT Bombay. He was my teacher, our teacher. That time, this was in the 1980s, the spectrometer came to IIT Bombay. He used to take night classes, evenings, 5 to 7 p.m. classes. He used to tell teachers. So that's how I started learning from him. Finally, I ended up doing PhD in that area. He's still alive, give him. I will put his photo next time. He's still alive. He is in Guwahati. He's not able to walk, but he is there. He was the person who was teaching us all this.
Apart from this binding energy, we can measure any magnetic studies with correlate this XPS data with UP.
That's a good question. The machine which is installed in a ARCI, it is possible to do that. It is possible to do that, but for example, magnetic, since you mentioned it, I should say, when high temperature superconductivity is measured, was discovered in 1987, 86, 87. The samples were made, and then the they tested the superconductivity. They are superconductors. If they cool it 80 degrees, 80 Kelvin. So I was doing that experiment also. I cooled the sample in the spectrometer by at 80 Kelvin liquid nitrogen temperature by passing liquid nitrogen through the probe and then measure the spectrum to see what is the difference between the magnetic field. So people try to do that. There are cases where they have been able to say magnetic effect can be analyzed using a XPS, but they have to do specific experiment. For example, in the magnetic materials, the magnetic domains are there. The domains will keep changing. Domains means, spin up, spin down domains are there. These domains keep changing with temperature and other conditions. So it is possible to do that. Right now, I don't have much information on that, but it is possible to do that. Okay, I'll include a few slides next time.
One more question, there is a dia and paramagnetic compounds, metal complexes are there. Is there any relation with here XPS and UV? UV also we are getting paramagnetism and diamagnetic, such compounds is there. For that such compounds, how spectra can vary for magnetic, paramagnetic compounds and diamagnetic compounds?
Yes.
If they are structurally different, then it will show indications.
No, generally, copper and.
But it cannot distinguish, I feel, diamagnetic and paramagnetic.
The XPS spectra can be different. Based on your complexes.
Yes.
For example, if you have high spin, low spin complexes, high spin, low spin complex, particularly cobalt, if I remember, cobalt 3 plus 2 plus, normally cobalt 3 plus should have higher binding energy, cobalt 2p if you take, but generally it shows cobalt 3 plus has a low binding energy. That is because of the electronic structure of the cobalt complex. There is a good example in the literature, right? So it is possible to do that, but it may not be, you cannot generalize it for everything. So when you observe such a thing, it becomes a kind of a research problem. We have to identify and then analyze it properly. Yeah. Whatever I have given you is the standard ones which are established. But a lot of things which you study, materials analysis, etc., you use the standard information. Sometimes, you will observe something new which may not be there in the literature. You will have to look at it and analyze it. The students.
Sir, online any questions, okay. Okay.
Same material, different particle size. Will it have any effect on the spectral signatures? It will not have, provided if the particle surface also should be same, should not be different. If you change the surface properties, nanoparticles and larger particles, you may have the surface may get modified.
This slide, is there a given?
Right. For example, if you see, okay, let me just give you this example. If I have one layer, atomic layer, second atomic layer, I can actually distinguish these two also. It is possible. Small changes will be there. Will be about 0.01, 0.03, 0.05 or 0.5 EV difference. But for that you need very high resolution spectrometer, the synchrotron radiation center, where have a very high resolution. It is possible to distinguish between atoms in different layers. It is possible. But our spectrometers may not be able to distinguish that. Similarly, nanoparticles also, if you have a smaller and bigger size, if there are any small changes are there because of this, it is possible to distinguish, but it has to be done very specialized experiment has to be carried out on that.
So there is no questions. We'd like to say thanks to Rangarao sir. Thank you, sir, for giving valuable information. Next time we'll keep you for 1 day, sir. For all. You can take next time we'll give you 4 to 5 hours. Okay, thank you, sir. Thank you. Sure, sir, we will. Okay, now, I would like to present a memento to sir. Thank you, please. The next session on XRD by Dr. P. Kupuswamy. Premchandra sir, sorry for inconvenience, sir, you also. Sir. Okay, Kupuswamy sir is about to leave, so, okay, thank you. హలో సార్ జీవి రావు సార్ వాయిస్ వినపడుతుందా సార్ ఆడిబుల్ సార్ సార్
Hello. Are you
So
able
my
to?
voice, yeah, thank you, sir. Thank you so much.
Yeah.
Dear participants, sorry for delay. Now, next talk on the next talk by G.V. Rao sir, G. Venkateshwar Rao sir. He is Deputy General Manager of Material Management at Doni Malai, NMDC. So he is going to give brief about some national minerals, metallurgic, such things. So with this small introduction, I would like to give session to the Dr. Rao sir. Sir, please proceed, sir.
Please 1 minute. Are you able to see my screen?
So please share, yes. The camera, okay, sir. Please share the screen, sir.
Okay. Wait, I'm going to give you my screen. Please be online.
Yes, sir.
Are you able to see my screen?
No, sir. No, sir.
No. 1 minute.
So if you have slides, you can send me same WhatsApp number. We will share if any.
Already I'll send it
difficulty.
to our Channakeswar sir. Yeah.
Uh-huh.
How to share this? Are you able to see my slide? Now is it okay? Are you able to see my slides? Mr. Ramanjaneya. Mr. Ramanjaneya. Mr. Ramanjaneya.
Yes, sir. Please
Are you
share.
able to
Please.
see my screen?
Yes, sir. Yes, sir. Please, sir. Hello. Yes, sir. Yes, sir.
Can I
Please
go
open
forward?
PPT, sir.
Ah.
No, yes, sir. Yes, sir.
Can I start?
Yes, sir. Yes, sir. Please, sir.
Yeah,
You can start,
good
sir.
afternoon. Welcome to the
Yeah.
workshop.
Sir, can you the PPT can you open, sir? PPT you can.
I have sent it to Channakeswar sir, and
Okay.
I'm right now it is on my screen. Are you able to see my screen?
Yes.
Are you able to see my screen? Mr. Ramanjaneya, can I go? Can I go forward?
So your now it's okay, sir. Now you can. Now it's okay, sir.
Now it's okay.
Okay. You can.
Shall I go
PowerPoint
to
mode.
uh,
PowerPoint mode.
PowerPoint mode, presentation mode?
Yes, sir. Yes, sir. G.V. Rao, sir.
Okay. Welcome to the workshop on interpretation of instrumental methods, organized by Satyabhama Institute of Technology.
So PowerPoint mode, can you say? PowerPoint mode.
Presentation mode you are asking, eh?
Yes, sir. Presentation mode, sir. Yes, sir.
Now? Are you able to get?
Yes, sir. Yes, sir. Yes, sir. Please, sir. Thank you. Thank you, sir. Now it's okay, sir.
Okay. So everyday life, we are going to see so many types of particles or materials. Materials are made up of various particles. And if we want to know about the materials, we should know about the particles. The particles we have to characterize. What is the importance of the particle characterization? If you see, anything like its quality, its productivity, its safety, and its process efficiency, everything depends on the quality of the particles. Quality of the particles can be controlled, can be increased or decreased depending upon the various processes what we are going to adopt. And you see, there will be so many advantages if you are going to characterize the particles. That will improve our product performance and product quality, and sometimes it will be helpful for us to reduce the cost and improve the quality. And sometimes various products will be innovated through the characterization. Coming to particle characterization, there are so many types of characterization in this. Maybe morphological characterization, structural characterization, compositional characterization, physico-chemical characterization, functional characterization, interfacial characterization, and transport and storage characterization. For each and every purpose, we have to characterize the materials. This materials technology totally depends on this particle characterization. If you are in a position to know what is that particle and what are the properties of that particle, what is the nature of that particle, then it is easy for us to develop a quality product and to reduce the cost of the product. Particularly if you are going for the morphology, there are mainly two things are there. One is size and shape. If you see, coming to the size, in our day-to-day life, if you take a wheat particle, if you take the suji, if you take the atta, if you take the maida, all are made up of same from starting in material is wheat. If you see, in each and every one, the energy levels are very high. The energy level in the wheat is less, and suji is high, and atta is higher, and maida is highest. But their initial material is only wheat. This I am giving you to understand the nature, and we are going to see this type of material day to day. Size is very much important for us. Here you see size matters. A particle, as I have given the example, wheat, it will be in around 5 to 6 millimeters, whereas suji, it will be around 2 to 3 millimeters, whereas atta less than 1 millimeter, and next maida, it is less than 1 millimeter. So with this, before going to size characterization, I would like to say once again, size matters. And how you will find out the size? For this one, we have to go for the size analysis. What is the importance of the size analysis? Here, if you take any product, you can find that product has been distributed through various sizes. And if you want to optimize any process, you should know the particle size analysis of the product process. And if you want to develop a new product, you should know what will be your product, what is the size of your product, what is your morphology of the product, what may be the shape of your product. Like that, In this product development also, size plays a vital role and size analysis is very much important. Coming to the quality control, it ensures product consistency adhering to the specifications. Then only whatever the product we are going to produce, that will be with a high quality and that will be useful for our customers. We know that size matters, but wherever every place this size matters. But coming to our day-to-day life, it may be in pharmaceuticals, it may be in food processing, it may be mining and mineral processing, cement and building materials, paints, pigments, environmental sciences, and cosmetics and material science. You imagine a particle or a product with a size around 1 mm. Whether can it be used to cosmetics? Our women and ladies, they will complain that this is not smooth, this is very rough when I am going to apply on my face or on my body. Hence, cosmetics needs very fine particles. If you coming to the mining and mineral processing, in the mining, the particle size will be around 100 mm to 1 mm size. Whereas mineral processing, most of the particles are less than 500 microns. And coming to the cement and building materials, you might have heard about the 53 grade cement and 43 grade cement. Why this nomenclature has been given? You please imagine, if I am going to use 53 grade cement, what will be my strength of that particular structure? And if I am going to use 53 grade cement, what will be the strength of that particular structure? If you want a good strength with a structure, it has to be built with the best material, that is 53 grade cement, which is less than 53 microns. Excuse me. And coming to the paints and pigments, if you see whatever the material we are using in the paint and pigment industry, it is less than microns. It is less than 100 micron size, such that it will be adhering to the mother material where it is going to be painted or pigment is going to apply. If you see in the environmental sciences, the aerosol particles, what we are seeing in our atmosphere, and if you see any locations, pollution control, that we will be seeing that one P25, P2.5 like that. This is the particulate matter less than that size. And what are the various methods used for determination of the size? Because we know that we already came to know that one, size matters. If size matters, what is the size? We have to know. If we know the size, we can apply that one wherever it is required. The very conventional method of size analysis is sieving. That is in the laboratory scale, whereas screening, that is in industrial scale. If you take any mining and metallurgical industry, screening will be done on industrial scale from 80 mm to 1 mm size. The size will be different for different particles. If you take a steel plant where we are going to produce pig iron. For this one, raw material will be iron ore, which will be having a size of 10 to 40 mm, and limestone 10 to 20 mm. Like this sinter, it is 10 to 80 mm. This will be crushed to required size and then it will be screened, and that can be used in the steel industry. If you coming to the laboratory scale, any type of powder, this can be screened by using sieves, laboratory sieves. That can be used from laboratory screens can be used from 40 mm to 500 microns. and less than that one, efficiency will be decreasing. Even though we can use up to 200 mesh, that is nothing but 75 microns, and that dry scale. If you want a perfect this one, it should be in wet scale. If you want a particle, a product or anything less than 35 microns, that can be particle size analysis can be done by using a cyclosizer, which is shown here in the bottom of the sieving. And other methods are air elutriation. It is very less used. And whereas microscopy, coming to the microscopy, we can determine the particle size by using optical microscope. If particle size is very less than 10 microns or something else, then we have to go for the electron microscope. Sometimes we can use liquid sedimentation is also for size analysis. And latest methods are there, something like dynamic image analysis, static laser light scattering, SLS, and dynamic light scattering. You see, compare the various particle size measurement techniques with their size range and advantages, disadvantages. You can see sieving is the coarse most particle size method, where you can sieve the particles or analyze the particles, or particle size can be measured up to 38 microns effectively. Less than 38 microns, we have to go for cyclosizer, and these are very easy, simple techniques. And next, if our particle size is less than 1 micron, then we may be going for the microscopy. In microscopy, we can go up to 0.1 micron to around 10 nanometer. If we are going to the laser scanning electron microscope, even we can go up to 1 nanometer also. And other techniques like laser diffraction, it is a size range is 0.1 microns to 2 millimeter. Dynamic light scattering less than 1 millimeter, and electrostatic aerosol analyzer is a submicron particle that can analyze particle size up to the submicron size also. You see, this is the cyclosizer. It will be having a 5 cyclones. It can separate the size particles from 8 microns to 43 microns. And you can see the various cyclones are there. Depending upon the size range, C1, C2, C3, C4, C5. Here we can get the 6 products here, starting from 43 microns to 8 microns. This is one of the process which depends on density of the particles and the temperature of the room. If the room temperature increases, these 43 microns may become 38 microns, and 8 microns may become 12 microns. Most of the times we used to say about surface area. There are 2 conventional methods to identify this one. One is BET surface area measurement analyzer, and one more is just like it is like a picnometer using this one. These 2 methods will be giving us the surface area. This surface area measurement will be mostly useful in the mineral processing and cement industry. If we compare this BET surface area and Blaine number, the principle of BET surface area is gas absorption, whereas Blaine number is air permeability. And measurement technique for the BET surface area is measurement of amount of gas absorbed on the particle surface, whereas Blaine number is measurement of time taken for a certain volume of air to pass through a compacted bed. units for this bead surface area is a meter square per gram, whereas units for blade number is centimeter square per gram. And application of this one is that BET surface area most of the times is used in pharmaceuticals and cement industry, whereas the blade number is used in mining, cement industry, and mineral processing. Particularly if you say iron ore pelletization, the blade number for this shall be 1400 to 2400. Coming to similarities of BET surface area and blade number, surface area measurement, in both the BET surface area and blade number, they provide the surface area of the powder. The powder fineness will be known in both the things, and the quality control in the BET surface area and blade number can be easily controlled, and based on that one, the product what we are going to get, that can be specified. If you see the units for this, nearly equal, but whereas blade number unit is centimeter square per gram, which is equal to 1000 times of a BET surface area, because it is given in the both are measured for gram, whereas area is measured in centimeter square and meter square. This is the overview of our NMDC pellet plant at Donimalai, Karnataka. With this, I would like to thank the organizers for giving me a chance, and I would like to thank all the who are patiently heard my lecture. Thank you. Over to Mr. Ramanjanaya. Mr. Ramanjanaya. Thank you for the organizers and all participants. Thank you. Ramanjanaya. మీ వాయిస్ వినపడలేదు రామయ్య గారు. ఐఎమ్ నాట్ ఏబుల్ టు హియర్ యూ.
Substrate is stronger, then the data fill.
Hello, sir.
Yeah.
Hello, sir. Hello, audible, sir.
Yeah,
Okay.
it is audible. It is audible.
Sir. Thank you, sir. Participants have any queries regarding session? Hello, participants.
I welcome the questions from participants.
Yes, sir. Participants, please, any questions or any queries? Okay, there are no more questions. Thank you, sir. Thank you so much for valuable information. Very informative lecture, sir. Thank you, sir. Thank you so much, sir.
Okay, thank you.
Thank you, sir. Anything would you like to say, sir? Your message, sir. Okay. Hello, sir.
Yeah. Ramanya Reddy garu.
Thank you, sir. Thank
If no questions, I will quit.
you so much, sir. For lecture. Thank you. Sir.
Okay, thank you. Thank you very much.
Okay, sir. Thank you. Sir. Thank you so much, sir. Sorry for interruption, sir. Sorry. Physical mode also going on, so we just. Sorry for sir.
Okay.
Thank you, sir. Participants, now we may have some lunch break. Okay, we will meet you within 30 minutes. We will update you next session. Thank you, sir. Thank you so much. Lecture வேண்டாம்